Every year, almost 2 billion tons of steel are produced worldwide. China is the world's largest producer, making 1 billion tons on its own. But do you know how this product is made? Watch this video to see all the stages of steel manufacturing, from raw materials to the final product. When you hold a stainless steel utensil, cross a reinforced concrete bridge, or simply open the refrigerator door, it's hard to imagine the journey that piece of metal went through to get to your hands. Steel, which is present in almost everything we build, comes from the combination of iron-rich rocks, high temperatures, and a great deal of accumulated knowledge. Steel has a long and fascinating history. It began thousands of years ago, when ancient blacksmiths discovered that adding carbon to iron produced a stronger and more flexible metal. Initially, production was handcrafted and limited to small quantities. But in the 19th century, with the Industrial Revolution, fundamental innovations emerged, like the Bessemer converter, created in 1856 by Henry Bessemer, which made it possible to turn iron into steel quickly and economically. Soon after, processes like the Siemens Martin furnace and later the basic oxygen converter in the 20th century further accelerated production, making steel available in large volumes and more accessible. Steel is a metallic alloy, mainly composed of iron and carbon, but it can also include other elements such as manganese, silicon, sulfur, phosphorus, nickel, chromium, molybdenum, vanadium, among others, to give steel specific properties such as corrosion resistance and the ability to be hardened. The production of steel begins at iron ore mines. The most well-known deposits on the planet are located in regions such as Carajás, in northern Brazil, Pilbara, in the Australian desert, and the Great Lakes Belt in North America. In this first stage, excavators dozens of meters high remove blocks of reddish rock that contain hematite or magnetite. Trucks transport the load to crushers that grind everything into small stones. Next, vibrating screens separate the fine material from the coarser one, and giant magnets remove non-iron impurities. The goal is to concentrate the metal content to a level that steel mills consider economically viable. The next step is called pelletizing. The iron ore powder is mixed with water and a natural binder, forming small spheres the size of marbles. After being dried in rotary kilns, these pellets gain enough hardness to withstand transportation. They are loaded onto trains, ships, and finally arrive at the plants. Meanwhile, another essential ingredient undergoes its own transformation. Mineral coal becomes coke. For this, the coal is heated in ovens without the presence of oxygen for about 20 hours. The process removes volatile gases and leaves a porous solid, rich in carbon, perfect for generating intense heat inside the blast furnace. We then arrive at the first monument of steelmaking, the blast furnace, a cylinder that can exceed 20 to 25 meters in height, lined with refractory bricks. From above, every few minutes, workers pour alternating layers of coke, iron ore pellets, and small pieces of limestone. At the base, blowers inject air that has been preheated in ceramic brick regenerators. Inside, temperatures easily exceed 1,500 degrees Celsius. The coke reacts with the oxygen in the air and forms carbon monoxide, which rises up the furnace column. Along the way, this gas steals the oxygen from the iron oxide, leaving behind liquid iron and carbon dioxide. The metal, now called pig iron, goes down and accumulates at the lowest part of the vessel, while the mixture of limestone and impurities turns into slag that floats on top of it. Periodically, technicians open a hole in the refractory wall and watch a luminous river flow into channels and then into torpedo cars. These wagons are real thermal flasks on rails, insulated with special bricks, capable of keeping the metal in a liquid state, faint liquid, during the journey to the second key equipment, the basic oxygen converter, known by the acronym LD. Inside an external steel shell and lined with bricks on the inside, the pig iron receives a jet of pure oxygen blown through a tube called a lance. In less than 20 minutes, the reaction reduces the carbon in the metal from about 4% to values close to 0%, turning the pig iron into steel. At the same time, new slags are formed that absorb sulfur, phosphorus, and other undesirables. However, there is an alternative and increasingly popular route in steel mills to produce steel: the electric arc furnace. In it, the main raw material is scrap metal, beams from demolished buildings, pressed cans, and discarded car engines, which go through magnets, shredders, and equipment for oil removal. Graphite gas electrodes descend onto the pile of scrap and create electric arcs so bright they resemble lightning. The temperatures exceed 1,000 to 1,700 degrees Celsius, melting everything in a matter of minutes. This method of production doesn't require coke or limestone and allows for the recycling of virtually every steel residue produced by society. Both the steel freshly produced from the basic oxygen converter and from the electric furnace go on to what's called secondary refining. There, inside covered ladle tanks, a vacuum system removes dissolved hydrogen and nitrogen, while argon jets bubble to homogenize the temperature. Calibrated additions of manganese, chromium, nickel, or niobium define specific properties. Some steels need to withstand weathering, others have to endure extreme heat or, on the contrary, be used for cryogenic tanks. The final composition follows an international standard, ensuring that the product reaches the buyer with predictable characteristics. Once the liquid stage is over, it's time to solidify the metal. The dominant method in the world is continuous casting. The steel flows through a cooled copper mold, forming a solid outer shell shortly after leaving the nozzle. As it moves down the rollers, the piece takes the shape of a slab, a square billet, or a rectangular bloom. Hydraulic shears cut precise lengths while the interior is still orange-red. It's a mesmerizing spectacle. Glowing blocks weighing dozens of tons sliding as if they were bars of soap, emitting white steam. In the next stage, these still hot slabs enter the hot rolling process. A series of rollers compresses the material, stretching and thinning it. Each pass slightly reduces the thickness, and water jets control the temperature to prevent the surface from burning. In the end, the slab becomes a long strip rolled into a coil, construction rebar, or a profile. With its shape defined, the steel can undergo heat treatments. Quenching followed by tempering hardens parts for tools. To face iron's greatest enemy, rust coatings are used. Hot dip galvanizing immerses sheets in liquid zinc. Industrial painting applies epoxy or polyester layers. In food applications, a thin layer of tin keeps cans free from contamination. In the automotive sector, complete electrodeposition lines create a protective film before the final painting. After being released, the material follows global logistics. Coils travel on dedicated ships protected against sea air. Rebars arrive by train at distribution yards. And that was today's video. Don't forget to leave a like and subscribe to the channel.